Yes. Okay. So the recording is now on. That's great. Yeah. So basically, I mean, with all of these probabilistic programming sessions, I try to give you a story to make some of the concepts and some of the equations that we go through throughout the course to make them a bit less abstract, to really tie them to physical quantity, things you can visualize and imagine. So this time I've used an archaeology story where we have some data set that's very hard to understand, but you can imagine that there might be some typing, some clustering going on in there, and you would like to find that. And so the Gaussian mixture model it tries to, in this case, we'll try to find types of stone flakes, and these should represent, or the hypothesis that they represent the evolution of this stone shaping process over time. We have a question. At the parameters of the kth component part, we calculate lambda and give this as variance to distribution of mu. Why do we not use lambda inverse? Right, so lambda is already the inverse. So lambda is the precision matrix. So we, let me see there. Yeah, so we define this like here to be a set of Gaussian components, and you can see here in this equation, this part, this is a Gaussian with the ith observation, and then we have a mu and a lambda. And so the convention, the standard that we use is that when you refer to a Gaussian distribution in this form with this this n notation, you are always using the well, if it's multivariate, you're always using the covariance matrix. So if lambda is defined as the precision matrix, and then here we've inverted lambda to produce the covariance matrix. So here we write this as lambda inverse, which represents the covariance for this component. And then here later on, when we were looking at each of the priors for these components, then we're talking about lambda itself. So lambda itself is part of Wishart distribution, and here for the prior for the mean, it also enters again as lambda inverse, as the covariance matrix. So lambda is defined as the precision matrix, and then whenever we have to describe something in terms of a covariance matrix, we use lambda inverse. Does that answer your question? Yeah, okay. Thank you very much. Thank you very much for the question. Yeah, sorry. Yes, so if you have any other questions on the implementation of this Gaussian mixture model, please, please ask them. We are getting into more difficult territory because well, before we've always had either one unknown variable or perhaps two. If you remember the classification problem with this local variational parameter. Now we have a lot more than one unknown variable. So we have each of the components, the component parameters, and then the assignment variables. But overall, it's still the same procedure. I hope that is clear from this notebook, from this description. And yeah, so the final results sort of make sense. You do see some clustering in the data, and the Gaussian mixture model recovers that. So the next question is, when iteratively training a non-Bayesian model, you can come across loss function plots that explode or see oscillations, for instance, when jumping around a minimum. It's possible to observe similar things with the free energy minimization. Yeah, so in sort of in frequentist statistics, we're using gradient descent as a maximum likelihood estimator. That's an optimization procedure, and you're following the gradient towards the minimum. In a lot of applications these days, where you're training these large neural network models, deep learning, deep neural networks, you would use something called stochastic gradient descent. So that's a variant of gradient descent where you're still following the gradient towards a local minimum. But there's a few, these optimizers or these gradient descent optimizers, they've been tweaked a number of times you have additional parameters such as momentum, which makes you sort of accelerate when you're going downhill, and then when you're going uphill, you still have some momentum, so you can roll over small hills basically. And those additional parameters are really useful for non-convex optimization in these deep neural networks, for instance. And they're sometimes they're very useful, but they can also be pathological. Yes, they can indeed cause these oscillations, and you just have to wait until one of these parameters, such as a learning rate, dies down, because they naturally degrade, and then you have to wait until it really becomes stable. So the thing with free energy minimization is that because this is sort of a subtle, nuanced point, but so we're updating each of these recognition factors iteratively, and when you observe this updating process in detail, you'll recognize something called a coordinate descent optimization procedure. It's a bit too much to go into now, but you can imagine that. So when I'm updating one recognition factor, I'm basically I'm basically changing part of the variables that I'm optimizing over, and when I'm changing or I'm updating another recognition factor, I'm changing a different part of the set of unknown variables. The thing with free energy minimization is that because we have these closed form updates for each of the recognition factors, you are always going to get a reduction in free energy through each of these updates. So first you perform an update in one of the recognition factors, so they'll give you an equal or strictly less. That's a reduction in free energy in that direction, and then you update another recognition factor, and then you have a decrease in free energy in a different direction, and so you'll move towards a local minima, and there's very little chance of oscillating. In fact, there's almost this is a much more stable process. It will not oscillate around the local minimum. Depending on your generative model, you will still have a non-convex optimization procedure. So you will hit local optima instead of global ones, but that's just unavoidable. That's just a property of the model. In this case, the Gaussian mixture model. But any sufficiently complex model will have a non-convex optimization problem. And in practice, when we're dealing with dynamic models, so things where we continuously stream in data and when we try to do inference with a limited time budget, and we have to proceed to another observation, these local optima are always perfectly fine. They're never pathological, and that always works out nicely. So, so does that answer your question a bit? So in free energy minimization, we have this property that they won't explode. There will always be a strict decrease in free energy through updating these recognition factors. It doesn't oscillate in the way that some other machine learning procedures, such as stochastic gradient descent for deep neural networks, might oscillate. But you will see tinier and tinier updates after over time. So here, for instance, you can see that the free energy decays really smoothly after 20 iterations, but there's still a very small decrease between each of these iterations. So yeah, it will approach this local optima, but it will still, it will not reach that point and then stay there. It's just a normal optimization process. You need some tolerance before you really, So once you reach a small enough neighborhood of the local optima, then you just call it quits, because it takes way too much computation to continue for such a small improvement. Does that answer your question? All right. Yeah, already I briefly mentioned this the second part as well, the dynamic models. So I used the situation of an alpine railway system. So it's a cart going uphill. You can of course recognize the stochastic process in this, but it's nice to have this idea that it's a cart going uphill, and it tries to maintain a constant velocity, but doesn't always do that. And you're just trying to estimate position based on noisy observations. So what I've shown you here is the yeah, we're just doing state estimation. So we basically, this is another recursive procedure. So for each time point, we try to estimate the state and then move on to the next one. And later on in the fourth probabilistic programming assignment, I've added a noise parameter as another unknown, and you'll have to simultaneously update, or you have to simultaneously estimate states and a noise parameter. But that's not as hard as it looks. There's a good description in the assignment. We'll get to that in a minute. So did anyone have any problems with the dynamic models? Did you all get around to having a look at this session? Yeah, so some yeses uh, and yeah, I can imagine it also takes a bit of time for the material to settle, and then some people have not managed to get that far yet. Yeah, so I mean, it's nice to see that you've had a bit of time to get up to this point. Of course, Christmas break helps, although I hope you did take time to rest up. Yeah, so perhaps this is I mean, so it is not a. You've probably been exposed to more complicated models than purely state estimation, or basically a filter. Um, but I can also imagine that it might be that not everything is clear for you yet. So feel free to ask. By all means, if anything is unclear, just ask away. Now is the time. Yeah, and one of the major components of what we're doing here, these Bayesian filters, is that you always get an uncertainty estimate for your state. So what we visualize here is the mode. So because we're using Gaussians, the mode is the mean. So we're visualizing how that evolves over time, and then we have this blue ribbon surrounding this mean function. The mode of the estimates at every time point. And this is something that you don't get with a recursively squares estimator, for instance. And it's useful for a number of purposes, but yeah, we haven't really gone into that here yet. So you can imagine that if you try to do some form of forecasting, so say you're working on a weather model, a weather prediction model, then you can imagine that as you unroll time into the future, that, well, similar to the assignment for the third probabilistic programming session, that your forecast is just going to widen up. So you can really see that your predictions are becoming more uncertain as it gets further into the future. So over the course of the yeah, so I just had a question that came to mind. So over the course of the well, of the course, I've interleaved parts of the probabilistic programming sessions with these try it yourself blocks. So if you've actually tried some things yourself, could you just post yes in the chat? That'll give me an idea whether these blocks are useful. So I'm trying to indicate whether these, yeah. So the whole point of the probabilistic programming session that you have some code for yourself to try out. You can play around. You can turn some knobs. Ah, it's really good to see that people tried this. Yeah, yeah. So you can develop an intuition for why, yeah, why these estimates turn out this way, right? So what if you change the prior? What if you put in some really large value, some really small value? And how does that affect your estimations? Yeah, do certain things become unstable? When can you break this? That's always a good intuition to have. All right, it's nice to see that people tried this. Yeah, I mean, there's many ways in which you could alter these procedures to develop an intuition for this. I'm just trying to sort of indicate the ones that will give you the most the smallest changes that'll give you the most insights. Yeah, so I have another question, more of a general question. To what extent are these probabilistic programming classes included in the exam? Well, perhaps Bert might say more about this.
Yeah, hi, this is Bert. Yeah, regarding the exam, there might be a question on probabilistic programming, and so the way it will be, it's going to be multiple choice. You're not going to have to program something yourself. The entire exam is going to be multiple choice. So you're going to be shown a piece of code, and then we can ask a question about it, right? It could be, let's say, what we're looking at right now. Well, yeah, something related usually to the model building, right, or the inference, but usually to the model building. So here you see some random variables that are being, so a model is being built, and a question could be like, is this, is this a valid model, or what's wrong with this model, something like that. And then 4 answers or 3, and then you have to pick the right answer. So that may be possible, right? It's actually quite likely. So if you want to get a really high grade, I would also study definitely the probabilistic programming sessions. I gave away as much as I can give away without actually telling you the question. Okay.
Yeah.
All right.
I think so too. Yeah. Yeah. So I would suggest when you're studying for the exam, I mean, I've not introduced any new material, so I would just go over Bert's lectures and material as much as possible. And then whenever you feel uncertain about something, whether you're still not sure about some of the components in there, have a look. Maybe treat it in the probabilistic programming session, and maybe there's a chance there for you to play around with some of the parameters, and maybe that'll reduce some of your uncertainty about this. And while you do that, while you sort of use probabilistic programming sessions to aid your understanding of the theoretical material, you'll get more than enough experience so that you can answer any possible questions on probabilistic programming on the exam. All right, we have another question. So regarding the new lockdown, are exams still going to happen on campus if this was indicated as your preference? I believe we've had an email that this is no longer an option.
No, it is.
But
It
again,
is.
it is still an option. Okay.
Oh, I didn't see an email that it's no longer an option. Last thing I know, it's you. If you signed up for on campus, you're still signed up for on campus, and so it will be held on campus. If you didn't sign up for on campus, of course, you're going to do it at home. But I think it's still scheduled to be on campus. In fact, I got an Excel file that I'll share today in Piazza, or it's a PDF or whatever. But it has a list of where everybody is scheduled to take the exam. So I'll share that today on Piazza. Of course, it can change any day, right? but we'll let you know. Worst case, and so I also said that last time, even if you do it on campus, so it might be that option gets cancelled for whatever reason, right? And the British variant may just be so contagious that okay, so it's not possible. And then everybody will have to take it online. So it might be a good idea to practice taking the online exam anyway, or at least go through the working with that tool, that Ans Delft tool in Proctario. Yeah.
Is the practice exam for this module on Ans Delft, or how can we practice?
Yeah, I mean, there isn't really a practice. The practice exam is there's a practice exam on how to use Proctario and Ans Delft, I think. There isn't a practice exam for this class, let's say with questions for this class. There's a practice exam on how to use the technology. And for the class, you just have your set of or let's say exercises. And yeah, that's basically your preparation.
But these are in a different format than the exam will be, right? Because they're not multiple choice. So would it be possible for you to give us like 3 or 4 example questions of what we can expect in the exam, so we know the format? Would that be possible?
Okay. Yeah, okay. I'll prepare a few questions.
Thanks a lot.
But it's got to be just a few, right? Because I cannot make up a whole second exam just to practice. But I'll show you some examples. And yeah, so having this is multiple choice, I think it's actually a bit of an advantage for you because it's you always have time to finish the exam, right? You can always just fill in some answers. But yeah, I'll post in Piazza a couple of examples. I'll do that.
All right. So if there's any other questions on the exam, feel free to ask. In the meantime, I am going to move on to the 4th probabilistic programming assignment. And then after I finish introducing this one, I'll go over the solution to the 3rd assignment. So this is the last probabilistic programming session on Friday. So we'll question what documents can we use with the exam, the Gaussian and matrix identities.
No, you cannot use any documents. I mean, you can write, of course, on let's say a blank piece of paper to do calculations, but you don't need any materials, and you shouldn't have access to any materials. Because if you need a formula, like a difficult Gaussian formula, let's say for Gaussian conditioning or something, it's a difficult formula, then I'll provide that on the exam.
All right, yeah. I hope that answers that question. So this is the final probabilistic programming session. On Friday, we'll have the amazing bonus lecture by Magnus Kaudal. And then we don't have any more sessions until the exam. So my plan was to next week, Wednesday at 3:30, where we would normally have our Wednesday lecture, I will upload a video with the solutions to the 4th probabilistic programming assignment. So they'll give you some time to, or maybe I'll do that earlier than that actually, maybe I'll do that on Monday. So they'll give you some time to do the assignment, and then you can still check your results through that video. And I'll keep grading the probabilistic programming assignments until the end of next week. So that's right before the exam. Right, so in this 4th assignment, we're basically going to alter the model specification for this dynamic model such that we are going to simultaneously estimate states and noise. So we've mostly done, well, we still have the Alpine Railway data. So, oh, maybe that should be removed. I've this is the release version. I can't remove this comment. I'll do an update after the after this session. So we've left the Alpine Railway scenario, and now we just have a standard random walk. So we have a set of states that evolve over time as a pure Gaussian random walk, and then we have observations, noisy observations of the current state. Yeah, again with Gaussian noise. So W is a process noise component, and V is a measurement noise component, and W has a precision parameter of tau, and then V has a precision parameter of gamma. That's all explained in this section. So we are going to basically take the model specification for the dynamic model from the fourth probabilistic programming session. Oh, that's this part, and we're going to add a means of estimating the process noise precision simultaneously. So that's also described here in this question. You'll have to, well, the only thing you have to do is adjust the model specification such that we now both have a state transition component, and we have something to describe the unknown precision parameter. I won't go too much into detail with this, but I'll basically already give it away. So later on, there's a few cells that test the format of your answer to whether this is a variable and everything. And then this cell is actually quite a long cell that does all of the steps after model specification. So it does the model compilation into an inference algorithm, and then it actually executes that algorithm. It also generates then all of the estimates and visualizes your estimates. So as soon as you change the model specification here, the rest is all taken care of. You just press run, and that should give you this fit to the signal. So again, we have this mode of all of the estimates, that the line, and then the ribbon that surrounds it is the variance at each point at each time point. And then this second graph is the estimate of the process noise precision over time. So I fixed the seed. Oh no, of course. Well, I've given you the signal itself, so it's not random generated yet. So this is the signal, and your estimates will have to fit this signal. That's basically it. This is 5 points. In previous assignments, you've had to do multiple things in order to get 5 points, and this is just, yeah, you just have to complete the model specification such that we will simultaneously estimate states and noise precision. Right. So if you have any questions on this, let me know. Next week, I'll post a video explaining the solution for this assignment. And again, like I said before, this is getting into the territory where we, in the lab, work on real problems. So we design filters for signals using, we design Bayesian filters for signals. Yes, so if there's any questions, let me know, and I will now move on to the solutions to the third probabilistic programming assignment. So I've had a few, there were a few things on Piazza where people asked questions about how to tackle this assignment. I've given a few hints here and there. It's your job is mostly to follow Bert's section on the predictive distribution, and it describes the entire derivation and what you actually have to implement to obtain that predictive distribution. So that's both a mean and a variance component. So in this assignment, you were given a signal, or a set of observations over time, and I wanted you to compute the mean. So the predictive distribution has both a mean and variance because it's completely Gaussian. And so first I wanted you to compute the mean of that predictive distribution, and then later on I wanted you to compute the variance, so that we end up with this this forecast where you can see that the line is a nice linear extension of this data set, and then the forecast widens a bit because we're becoming more uncertain over time. So the answer, the computation for the mean is quite straightforward. You might have seen this before in a number of components. I think this came up in at a few points before, and then there weren't really any questions on Piazza about this, because I think this is clear. So the X bullets are all future dates. So those are scalars, and then we add these ones to be able to, so we augment this vector so that we can define the regression function as a dot product. And then we needed this m theta. These are the mean of the parameters that we estimated. Yeah, so that concludes the mean of the predictive distribution. So the variance of the predictive distribution, this is where most people got into trouble. So the main thing to realize is that at the moment the derivation, burst derivation, is for a single X bullet for a single future time point, a future sample. And what we're dealing with here is that we have 10 future samples. So we have to iterate over each of those samples. So you shouldn't treat X bullet as a vector and then perform an operation using that vector. You should take each of those components. So here I've done that with this list comprehension. So X bullet is a set of future dates, and then we iterate over those. So we pick each element iteratively, and then I augment each date in X bullet with a 1 to be able to conform to this this augmented covariate description. And then we implement the function that Bert described at the end of his derivation for the predictive distribution. It's a quadratic function of the X bullets with the variance of the parameters that you estimated, or well, that were already estimated here. And then we add the process variance term. So in Bert's derivations, there's a beta inverse. So beta is the precision parameter there, and beta inverse is the inverse of precision, so that's the variance parameter. And so here I defined, in the model specification, I defined a variance term instead of a precision term. So the variance of the likelihood is sigma squared y. But I set this to 1. So even if you forget to invert that 1, that doesn't matter, because 1/1 is still 1. Yeah, so you perform this computation for every date in the X bullet list, and that gives you the variance for each of the future Y bullets. Yeah, which produces a nice forecast, I think. Right, so I hope this is clear how you compute the predictive distribution of a Gaussian in a regression setting. If there's any questions, yeah, let me know. I'll try to fill up a few more minutes. Yeah, so again, after this session, I'll download all of the submissions, and then I'll start auto-grading them. And you should be able to get your grade or your feedback sometime tomorrow. I don't see any questions coming up, so I think that most of it has been answered. Right. Oh yeah, there's one. Does it check as correct if you manually write the +1? Oh, so I mean, do you mean if you write +1 here, so instead of sigma squared y?
Because I didn't write it as the parameter, but I looked up what the parameter was set to and wrote the +1.
Yeah. No, that's absolutely fine. So it so this particular piece of code, this list comprehension, produces an array, well, a vector actually of values, and the hidden test checks the values up to 0.1 precision. So oh, actually that's the sum over those. So that divided by 10. So it's up to a 0.01 precision. And yeah, so it doesn't matter whether you used 1 or sigma square, because sigma square equates to 1. So I don't check the syntax of your answer. I check the computed values, as you can see here. Any more questions? So the first two probabilistic programming assignments were perhaps a bit easy still. Well, the first one was especially easy. I think the second one was definitely a step up. This one was again a step up, and the next one, the fourth, is another step up in difficulty complexity. I'm going to take this time to get some feedback from you. Are you happy with the difficulty of these assignments? You want it to be more complex, maybe perhaps a bit more text or more explanation, or is it useful at all? Does it help you understand some of the materials, some of the equations?
Like, it's definitely good to work on the things again, because like if you just listen to it, it feels like you understand everything, and then when you have to do something, you realize what you understand and what you need to look at again. That's handy.
Yeah. Okay. Well then, yeah. Thank you for the feedback. Then it had the intended effect.
And one more question. You said it has to be implemented as a for loop.
Oh no, it doesn't have to be implemented as a for loop. It just so happens that I've implemented here as a for loop. What I need is a list of 10 values, and that list has to be in the format of a vector of floats.
Would what I now paste in the comments, would that do the same thing? Because I'm not sure if that does, but
Okay, so this is a vector times a ones vector that's been transposed. So this is an outer product. So this produces a matrix. Matrix times
like it is basically the X bullet concatenated with a ones vector. So like it's basically vertical, the X bullet and the ones, then multiplied by the parameter by the covariance matrix, and then again by this X bullet and ones concatenated as a horizontal vector.
It depends on whether you. So I'm imagining. So far y bullet will now be a matrix, and I imagine that this assertion will fail, because if it's a matrix, then this array of floats will. Well, the type of your answer will be array float 64-2, and so this assertion will fail before you get to evaluating this point. So you could. I would have to double check this, but I think you could take the diagonal of your answer, the far y bullet, and then I think that will produce this list. Although I'm not entirely sure.
Maybe I can join this discussion, because I did the same approach, and indeed I implemented the diagonal, and well, at least visual pixel by pixel, I came to the exact same result as you did.
Okay.
So indeed the diagonal together with Schmidt's approach would lead to the same result.
Okay, yeah.
Like I don't know why, like it doesn't fail when I run it, so like it.
Okay. That's odd, because it should. Is there anything else that you do with far y bullet after you've computed it this way? Do you slice it somewhere?
No, I like but I can just copy the entire block and like ignore that the fact that I commented out things, that's things that I didn't know what I was doing and like tried it.
No, I'm happy you tried a lot of things. That's how you develop an intuition for things. Right, yeah. Okay. So the visualization, I think, will work because the plot function implicitly will do something with a matrix ribbon. But when you run the so you have your answer now. When you run the assignment, so do cell run all or kernel restart and run all. Does this cell produce an error for you? I mean, it should. If it doesn't, then something's happening which I'm not
I
aware
don't
of.
think it did. Like I like I think it didn't.
All right. Well, then I'll take a look at your submissions manually to see whether what is happening there.
Okay, thank you.
Yep. Are there any other questions on this assignment? Okay. Yeah. I'll try and talk for a few more seconds. Yeah. So in the past, we've had a few discussions on whether you would actually need, or what is the use of estimating a posterior distribution instead of just a point estimate. Well, I think the uncertainty that you get here is very valuable in when you're communicating your results to other people. If you work with, for instance, clinicians in a medical setting, they will always want to know how sure you are. If you're, I mean, the number doesn't tell them anything. You want to know, they want to make it. They want to be able to make a statement to a patient saying, with some uncertainty, we can conclude that, or we've decided to take on a particular procedure or something. Or like weather prediction, that's still a good example. That you want to know, well, I mean, is it going to rain tomorrow? If you have a lot of uncertainty for that, then nobody can really blame you for if it doesn't turn out that way. And as you can see here in this computation, you really need a full posterior distribution for the parameters and coefficient to be able to produce this forecast. The only other thing that just came to mind that I would like to mention about what we do here in these probabilistic programming sessions, I forgot whether I actually mentioned this during the recordings. So over the whole course, I've shown you one toolbox, one software package called Fornilab. That's the one our lab develops. It's a tool for message passing and variational Bayes and exact Bayes as well, with some product message passing. Note that, so the thing I would like to say is that we're not teaching you how to just deal with or work with Fornilab. What we're trying to do is teach you something much more broader than that. The machine learning community is converging. It's moving beyond the deep neural networks into more hybrid probabilistic models, where some elements are perhaps non-parametric and deep learning based, because that's a very powerful tool, and other parts are very probabilistic because you've seen that in this course. It's just a form of reasoning from first principles. We have all this uncertainty information, and there's other properties like robustness to overfitting, and being able to rely on a prior when you have very few samples, that sort of stuff. So the machine learning community, or when you graduate and you move into a company and they would like you to implement something, a model, using machine learning, there are other software packages and other tools out there in different languages. In almost every language has a number of machine learning toolboxes. The communities are all converging on sort of a general, general is the right word, a language for specifying probabilistic models. So what we show you here with this macro for the random variable, and then this operation where we have some variable, then a tilde operation, and then a distribution, as opposed to sort of the classical way of defining variables, as in a name equals a number. This is now a name follows a distribution of some parametric type. That's very common, and it's going to be even more common as machine learning as a research field evolves. So don't think of this as sort of tutorial for how to use Formulab. This definitely is more widely applicable than just Formulab or Julia. There are other programming languages and toolboxes that use a similar format in specifying models. All right, if there are no further questions, then I'm actually going to stop the session, the lecture. I'll first stop recording.